Hmm. Decisions. Decisions. Dang. Yep. Park right here. Hold on, let me not park like a moron. Is there anyone coming that way?
No.
Okay, it's July 26th?
Yep.
2018. We are going to go on a short hike today. I was pretty correct with not knowing the geology about the area with the Grinnell Falls Trail or Grinnell Glacier, whatever trail that is. But I did pick this up and this helped, and we're going to go see some of it. What I'm standing on here is Cretaceous. Now up there is Precambrian. Well, Precambrian is older than Cretaceous. What's up with that? Well, we have something, we're near the front of what's called the Lewis Thrust Fault right here. So the Precambrian rock was thrusted up over the Mesozoic deposits in the area. And the falls should be the Precambrian. Now, when I talk about this, since I'm not gonna have this book open with me, and I can't remember these names for the life of me, the basal exposed Precambrian formation is a limestone. I'm gonna call that the basal limestone. Then there's the green and reddish black shales, which I can refer to as the middle lower shale. And then the stuff, the real pretty stuff that's red with white quartzite, I'm gonna refer to that as the middle upper shale. And then that limestone on top, I'm gonna refer to as the upper limestone. So, Sarah, just pan around to show the view. The flat flowing areas, like I said, are Cretaceous, and that's all Precambrian. Anyway, as we get closer, you can see here, like I said, we're at the leading edge of a thrust, the Lewis thrust, and it's a low angle thrust fault, very low angle. If you look at the beds here, you can see the bedding. They're pretty level for being thrusted over. The parts you see like here that kind of looks like that, that's not a fold. That's just the topography sticking out, making it look like a fold. I am going to try to get some measurements if I can when we get to the actual falls, but it's just kind of surprising me how level these beds are at the leading edge of a thrust. Hey, I'm not seeing the lava sill here, so I don't think it's here. That's fine. Getting there. Well, we found the falls. I'm trying to get the GPS. And there's the area where that fold is. Where that thrust fault. Sarah's gonna get some better pictures, see if I can see any brecciation or something like that. Let's see. Get a clearer picture of it now. I'll show you in a sec, yeah. Okay, let's see. Let me see. Okay, this right here looks like an anticline. But actually, you can tell those dark beds, as same as those dark beds, this is waste. This is just landslide. Over here, I'm not sure. I can't tell from here if that actually is a thrust fault that comes down and under. It looks like it might, because it looks like we have something over here. Or if that also is just slump. But Not seeing any beds above it that seem to obviously match, but I'll have to wait for Sarah's pictures to actually determine that. This is a view of the landslide, the slump. A little closer. Falls are right behind there. Still can't tell if that further one's thrust or not. I'm looking for it down here. I'm not seeing anything. That looks like slump. You can tell. Okay, see this features here? You color coordinate here and match it up here. So that's slump. It fell right from there. And the good thing about the Precambrian formations here is the limestones have like no iron in them. And some of them are actually dolostones. But the shales have a lot of iron in them. So the color here, kind of, even from a distance, you can tell the different formations. Now, here's a good shot. Here, lower limestone, you can see the tree line of contact. And then you get the red and green shales above it. Yeah, right there. Or the, not red and green. Yeah, the red and green, the lower middle shale. And then up top is the upper middle shale. So color is a way to kind of at a distance here, at least with these 4 formations, to discern what is what. Stromatolite. The lower limestone has tons of stromatolites in it, the upper not so much. And this is a good one. You can see a cavity formed in the middle. We've got some good calcite crystals. I'll just get a GPS of that real quick. I mean, it's totally out of place and everything, but it's just cool to see. Look at this block, Sarah.
That's what I was trying to...
You want to, can you tell what they are? You look on this side of this detached block and you see these big round things that look like pillows here, and that's what Sarah suggested they were. But you look here,
Are they ripple marks?
That's the top. No, not ripple marks, stromatolites. See? See? Right? All up and through here. You gotta get some good pictures of them. Yeah, that would be the top, because that's the top of the mounds. This is all stromatolites, this whole thing. It falls right past there, but see right here, that looks brecciated. And this is where I thought the thrust would come down if it was. And you see kind of a sharp looking contact between more massive, finer grain limestone and laminated limestone right here. So this may actually still be a thrust. I'm gonna try to get up there and get some measurements. This block does not look detached. Let me get GPS. Sorry, I'm in the way. Okay, in my infinite wisdom, when we came up here, I did not set my button to account for magnetic declination. So it's still set to what it is in the UP. But that's all right. I wrote that in my notes, and that can be easily compensated for. So strike will be slightly different. But anyways, I'm looking northeastish right now. And what I thought was the brecciated contact, if you look right here, you see this zone right here? This is what I thought the breccia was. But you look at it carefully, and you see little geodes, and you see stromatolitic structures in it. Some almost chert-like. You see some just normal laminations here. You see no evidence of breccia. And down here you see big stromatolites. So this, I now think this is some sort of diastem, some sort of, just missing small bit of time. There's some chert here too. But I do not think that this is a fault contact. I mean, it's quite possible right there, but see, there's lamination. There's nothing that would identify that this is a fault. And this is why, when you're studying geology, you need to get your butt up on things and look, not just try to do things remotely, because if you just do rely on that, you can come up with a totally bad interpretation. And I almost did that right here. Now, like I said, there is still a chance that this is the thrust fault, or the thrust turns and goes down and is beneath me and I don't see it. But this contact right here has about a 10% chance of being a fault contact. 90% chance of being a diastem, where your environment changed from one friendly to stromatolites to less friendly. And wait, GPS. Yeah, below that diastem, just loaded with stromatolites, mats, and mounds. And then right up there, it's the diastem. over there. We'll get up there in a second. Okay, so the waterfall is all within the basal limestones. And if you look, you can see you get massive ones with thinner argillaceous lithographic limestones in between, which tend to weather out a lot easier. But there's something else I noticed just sitting right here. And you've got the cool ripple marks that you can see. But you got that stromatolitic layer, which is almost 3 feet thick. But then you notice this right here. This tip follows this part right here that curls up. Right here, curls up. This follows the strike and dip of the rest of the rocks. They don't vary that much. But the actual strike and dip of the curves, actually, well, the curves I didn't measure because I can't. But it could be a small, tiny fold. That could be an unconformity. But like, so this is stromatolitic. I don't think it is. I think that's just a some sort of storm rip up or something to that effect. Structure, however, if you look at the top, I've been up there too. If you look at the top of the stromatolite bed before it gets back into lithographic ripple mark limestone, there is this thin layer on top, less than an inch thick on top that's cherty, and it's gray and white chert. It looks kind of brecciated, but that doesn't necessarily mean that this is some sort of tectonic structure, although it could be a little. I mean, if this would have been thrusted up that way, so it makes sense that that would be bent. So what kind of environment was all this lower limestone deposited in? Well, it was definitely near shore. The fact that you have stromatolites are photosynthetic. They need sunlight to survive and thrive. So that means tidal flat, likely. I mean, but these are definitely marine. The way the nice symmetrical ripple marks, and all the ripple marks here are symmetrical, and from crest to crest is generally no more than 2 inches. From 1 to 2 inches is crest to crest. They're very, even up section, they're very consistent. So this indicates a tidal flat environment, a slowly subsiding basin.
Right?
They're algae.
Oh, they are.
They're photosynthetic algae, and they're still around today. They exist as these domes, like in Australia, like they would be, domes. And they also exist as mats. There are saltwater and freshwater versions. Actually, I should try to, let me get a GPS on this boulder just for namesake. Obviously, it's not in place even. It's a top. It's no bedding plane. Let's see, GPS here. I don't know if I'm gonna take a picture. I don't know if that's showing it.